In the last video, we ended on the topic of inverse functions. We gave the definition of an inverse function, and we kind of looked at one example, and I'm going to go back over that example briefly. We have these 3 points, and what we said is we can think of these 3 points as a function where the domain is 1, 4, and 6, all of the x values, and the range is 2, 3, and 8, all of these y values. And the function says 1 goes to 2, 4 goes to 3, and 6 goes to 8. And we said we can write this as f of 1 is equal to 2, f of 4 is equal to 3, and f of 6 is equal to 8. So this is our function f. Now, if the function is one-to-one, which this function is because all of the y values are different, so we don't repeat y values, then we can talk about an inverse function. And an inverse function reverses this relationship. So this time, 2 will go to 1, 3 will go to 4, and 8 will go to 6. So our inverse function, which we label as f with a -1 in the power, f inverse of 2 is equal to 1, f inverse of 3 is equal to 4, and f inverse of 8 is equal to 6. And we can write this as a set of points. We have 2, 1, 3, 4, and 8, 6. So if you compare this set to this set, you can see that all of the numbers are just reversed. So that would be an inverse function when we're just dealing with 3 points in the domain and 3 points in the range. So again, an inverse function is just the opposite relationship of the actual function. Let's look at another example. This time I gave you 4 points. The points 1, 2, 4, 3, 6, 8, and 7, 2. First off, I want to figure out if this function is one-to-one. Now notice in the points, I have a 2 here and a 2 here, which tells me that this function, it is a function because we're not repeating points in the domain, but I do have the fact that f of 1 is equal to 2, and also f of 7 is equal to 2. Because this function is not one-to-one, that means it doesn't have an inverse. And why is that? Well, we could draw a picture here as well, where I have 1, 4, 6, and 7. Those are the numbers in the domain. And 2, 3, and 8. Those are the numbers in the range. Let me make that 8 a little bit clearer. And we can say that 1 goes to 2, and 7 goes to 2, 4 goes to 3, and 6 goes to 8. So this is our function, but if we try to reverse it, I really just want to focus on this number 2. Because if we reverse this, 3 will go back to 4, and 8 will go back to 6, but we have a situation happening right here. 2 will go to 1, but at the same time, it'll go to 7. So we have a problem with that, and why we have a problem is because this is not a function. So if you wanted to define this as an inverse function, well, it's not a function because we have this number being sent to 2 places. So the only time you're going to have an inverse function is when the original function was one-to-one. And notice also that when your function f is one-to-one, your inverse function is also one-to-one. Okay, let's move on. So the next thing we're going to look at is we're going to look at actual equations of functions, and where we don't just have a finite number of points in the domain and the range. So before we get to that, I want to tell you about some important properties of inverse functions. So suppose f is a one-to-one function. So if you have a one-to-one function, then your inverse, f inverse, exists, and it is also one-to-one. I mentioned that just a minute ago. So a one-to-one function has an inverse, and that inverse is one-to-one. Another really important property is that the domain of your function f, that is actually going to be equal to the range of your inverse function. And the range of f is going to be equal to the domain of your function. Let's scroll back up just for a second to verify this, at least with the last two examples here. Well, actually this example here. We said that this was our function and the domain was 1, 4, and 6. Well, look at the range of the inverse function. It's 1, 4, and 6. And the range of the regular function was 2, 3, and 8. And then the domain is 2, 3, and 8. So you can see that the domain and the range are flipped. This is actually a very important property because, you know, when I ask you for the domain and range of a function, if you're just given the equation of the function f, you can tell me the domain, because all you have to do is look for like square roots and fractions, and you'll be able to tell me the domain. But if I ask you for the range, just looking at the function, you wouldn't be able to tell me unless you knew what the graph of that function looked like. If you would graph it with a graphing calculator, then you could tell me the range. But just by looking at the equation of the function, without having any idea of the graph, you wouldn't be able to tell me the range. However, if you knew the equation for the function of the inverse, and you knew what the domain of that was, well, then you could give me the range of the original function. And that's something we're going to see a little bit later. Okay, so we talked about the domain and the range. Something else I want to mention is that the graph of f inverse and f are symmetric about the line y is equal to x. Now we've talked about a function being symmetric. We've talked about it being symmetric about the y-axis and the x-axis and about the origin. But now we're going to have a graph that may or may not be symmetric on its own, but if you want to graph the inverse, then you just reflected about this line y is equal to x. And then we're going to look at some examples in a few minutes of that. Another important property is that if you compose f with its inverse, what you're going to get is just x. And also, if you take f inverse and compose it with f, you'll get x. In fact, you can check to see if two functions are inverses just by composing them. And when you compose them and you get x, both ways, you have to do f composed of if you had two functions f and g. If you did f composed of g and got x, and g composed of f and got x, then you could say g is actually the inverse of f. And we'll see that a little bit later as well. So here's our next example. Let's find the domain and range of f and f inverse, and let's also sketch f inverse. So here I haven't given you an equation for f, I've just given you a graph. But from the graph we can get a lot of information. So you can see this is the graph of y is equal to f of x. Remember that the domain is how far left and right you go. So let's put f here, and the domain, actually let me move it a little bit to the right. I'm just going to use d for domain. The domain of f is what? Well, the furthest point to the left we have is this -2, -1. And the furthest point to the right we have is this 0.21. Remember, domain is looking at the x values. Because these points are colored in, I'm going to use a bracket. So we go from -2 to 2. And the range of f, remember that is how far up and down we go. So the furthest point down is also this point, and the furthest point up is this one. But this time we're going to look at the y values, which are -1 and 1. Now let's use that property I mentioned a little while ago about reversing the domain and range of our inverse function. First off, is this function even invertible? Well, the answer is yes. Why is it invertible? Because it passes the horizontal line test. HLT, I'm going to abbreviate it. So it's invertible because it's one-to-one. So a one-to-one function is invertible. Okay? Now, because it's invertible, we can talk about the domain of F inverse and the range of F inverse. I'm going to just tell you what they are using that property I mentioned before, but we're also going to graph it, and then you'll see the domain and the range. So the domain of F inverse is the range of F, so it's -1 to 1, and the range of F inverse is the domain of F, so that's going to be -2 to 2. Now let's graph the inverse function. So what I'm going to do is I'm actually going to draw a dotted line, and that dotted line is going to be the line y is equal to x. Now y is equal to x goes through the origin and has a slope of 1. So it goes through 0, 0, 1, 1, 2, 2, 3, 3, and also through -1, -1, -2, 2, and so on. So let's just draw a basic dotted line here. Okay, to give us an idea. So the graph of the inverse is going to be this graph of y is equal to f of x flipped along this line. And let me show you why. Because remember what happens, when we find the inverse, like here's a point, remember that the x and the y coordinates get flipped. So this point, -1, 0, will go to 0, -1. So let's find 0, -1. That's right here. And this point, -2, -1, will go to -1, -2. So here's -1, -2. So it goes right here. This point, 2, 1, will go to 1, 2. So we'll graph that. Let me erase this here. And notice that these aren't just the only points. We have the points in between here. So all of these points, if we reverse the x and the y coordinates, they'll get mapped here. And all of these points here will be mapped like that. And you can see that this map here, this function, is the mirror image of this one along this line. Okay, so this is the line y is equal to x. And you can see that this is the function y, let's call it a different letter. Let's just call it f inverse of x. Okay, so we've sketched f inverse, we found the domain and range, and let's also verify this. Let's look at the domain of this function, this red function. So remember, domain is how far left and right you go. The furthest point to the left is this one, which corresponded to this one, and this we said was flipped. This is -1, -2. And then the farthest point to the right we go is here, which corresponded to this one being flipped, which was 1, 2. And you can see that the domain is from -1 to 1, just like we expected. And also the furthest point down is this one, and the furthest point up is this one. And that corresponds to these y values, which are -2 and 2. Okay, let's move on. Here I have some more pictures. These are actually pictures from the book. I'm going to make it a little bit bigger here. And let's just do a couple of them. I'm going to do, let's see. Let's go with this problem. Actually, not that problem, because that's usually the odd problems are problems in the homework that you'll have to turn in. So 48, and let's also do maybe this one, 46. I'm going to draw the inverse function in red. So in these problems, the graph of a one-to-one function is given. Draw the graph of the inverse function. So for this one, remember, the inverse function is the mirror image of this with respect to this line y is equal to x. And we can show that this is a one-to-one function because it passes the horizontal line test. So the mirror image of -2, -2, well, we flip these two, is going to lay right there exactly on this line. It's also helpful if you could, sometimes I get confused with like, oh, does it go here or here or something like that. So just flip these points. this will go to -1, 0. So we plot that, and that goes here. And then we can just connect these two like these are connected. Okay. And then we want to go from 1, 0, that will go to 0, 1, which is right here. And then this is 1/2, 2 1/2, which will go to 1/2, 2. So 1/2, 2, which is right here. So it looks like the mirror image looks something like that, which does kind of look like a mirror image. Let's try this one. Again, this function is 1 to 1. Pass a horizontal line through it, only hit the graph one time. And then let's focus on these two endpoints. This is -2, 1, so it'll go to 1, -2, which is down here. And this point is 1, -1, it'll go to -1, 1. So now we just need to connect this. And this point is going right through the middle. That will also go through the middle. So looks like, so this is kind of going downward and this is upward. Remember to kind of think about the mirror image here. So that mirror image will look something like that. Great, let's move on. So the next thing we're going to do is we're going to actually look at equations for a function. So how do we find a formula for f inverse if f is given? So we may or may not want to graph the function. We just want to know the equation of the function. So there's a process you'll have to go through to find that equation. So here is our first example. Here I have a function f that is x plus 2. You might want to verify that this is 1 to 1. It is 1 to 1 because it's the equation of a line with slope 1. It goes through the point 0, 2, that's the y-intercept, and you can see that it'll pass the horizontal line test. Also, you can't ever get a repeated y value for anything you plug in here. Okay, so what we're going to do is we're going to write this as y is equal to x plus 2. Now remember what an inverse function does. It switches the x and the y. So that's what I want you to do first. I want you to switch x and y. So you get x is equal to y plus 2. Then your next step is to solve for y. I guess you don't really need an exclamation mark, but okay, so let's solve for y. So to solve for y, we just move over the 2. So I subtracted 2 and then I just flipped it so the y is in the front. Now when you do this, instead of you writing y, you're going to substitute f inverse of x for y. So we have f inverse of x is equal to x minus 2. And this is the inverse function. So all we do is we switch x and y, solve for y, and then replace y with f inverse of x. Now, how can we verify that this is the inverse? Well, there's a few things we can do. There's lots of properties of these types of functions. So one of them is we can graph and see if the graph is symmetric about the line y is equal to x. So maybe we should sketch this. I'm also going to sketch the line y is equal to x. Okay. And then I'm going to, let's sketch f first. Let's put that one in white since it's already in white, that color. X plus 2 is, well, it's up 2. So 1, 2. And it looks something like this. This is f. And let's do this function in red. It's x minus 2, so you go down 2. So you can see that these lines are parallel. And this line, if you flip it along this line y is equal to x, you get the one on the bottom. So they do look like inverse functions. Also, something we can do is we can check that f composed of f inverse of x is equal to x. I'm going to do that very quickly just for this particular example. I'm going to take f and I'm going to plug in f inverse inside. which is taking f and plugging in x minus 2. Well, the function f is x plus 2. So this is x plus 2, but instead of x, I'm putting x minus 2. And you can see that these two 2's cancel and we just get x. So we got this. This is correct. And we can also check that f inverse composed of f of x is equal to x. So this time you plug into f inverse f of x, which is x plus 2. So remember that f inverse is x minus 2. So x minus 2, but instead of x, I put x plus 2, and we get x again. So we do satisfy that property of f composed of f inverse, and f inverse composed of f gives us x. Okay, let's try another example. For these problems, I want to verify that the functions f and g are inverses of each other by showing that the composition is equal to x. And give any values of x that need to be excluded from the domain of f and the domain of g. So I've highlighted 36, 40, and 44. So let's start with 36. I'm going to copy it down here. F of x is equal to 3 minus 2x, and g of x is equal to negative 1/2 x minus 3. Now, we could have just been given this function and try to get it to this one. I'm going to do that really quickly, only for this example, just so you have more examples of it. And later on, we're going to do, I guess, harder examples or more examples. So what we do to show that this is actually the inverse function is we said, well, we take this function, we set it equal to y, switch the x and the y, and then solve for y. So this is x minus 3 is equal to negative 2y. So we can flip this. Negative 2y is x minus 3, and then divide by negative 2. So we get y is equal to x minus 3 over negative 2. And you can compare this with this one here. This one just has this negative 1/2 written in the front. So they are inverses. But what this problem wanted us to do was to actually compose the two functions. So let's do that for some practice here. Okay, erase all of that. So let's start with f composed of g of x. Well, this is f with g plugged in, which is f with negative 1/2 x minus 3 plugged in, which is, well, f is 3 minus 2. Now I'm going to plug this one in, negative 1/2 x minus 3. This is 3. Well, I'm going to send in this negative 2. If I send it in, this negative 2 and this negative 1/2 becomes a plus 1, x minus 3. So this is just 3 plus x minus 3. These cancel, and I get x, which is what I wanted. Now let's try g composed of f. Okay. So g composed of f of x is g with f plugged inside, which is g of 3 minus 2x, I'm plugging this in, which is equal to, well, g is negative 1/2 x, I'm going to put a big space for x, minus 3, and where I see x, I'm plugging in 3 minus 2x. Okay, so I can simplify this part in the middle because these parentheses aren't really necessary. So I have a 3 minus 2x minus 3, that's negative 1/2, and I just get a negative 2x, and then this just becomes x. So that property of g composed of f equaling f composed of g, which is equal to x, it works here. So they are inverse functions. And usually when this happens, when you have inverse functions, you don't put g, you put f inverse. I want to look at a couple more complicated examples. That's 40 and 44 here. So first off, problem 40, if we didn't have this x greater than or equal to 2, this wouldn't be a one-to-one function. Let me explain that in just a second. I noticed that I didn't talk about the domain of f and g here. That was part of this problem. So notice that both of these are equations of lines, and because they're equations of lines, then the inverse and the function, their domain is both all real numbers, okay? And because looking at this, the domain of this is all real numbers, that's the range of this function. So if I asked you, just by giving you this equation, what the domain and the range is, you say the domain is all real numbers because this is the equation of a line. And also the inverse is the equation of a line. So its range, this function's range is all real numbers. Okay. So focusing on problem 40, let me write it down here. We have f of x is equal to x minus 2 squared. And we're only focusing when x is greater than or equal to 2. And then we have the function g of x is equal to the square root of x plus 2. Let me get rid of all of this down here. Okay, just so I have some room. First off, let's look at a graph of this so we can understand why we're making this restriction. What is the graph of x minus 2 squared? Well, notice that the parent function is x squared. So this is taking the parent function x squared and moving it to the right 2 units. So it looks something like this. This is the graph of f. Now this function is not one-to-one. So what they do when a function is not one-to-one is you make a restriction. So you get rid of part of the graph, and by getting rid of part of the graph, you can make it one-to-one. If I get rid of this section right here, then this piece, which is just half the parabola, that is one-to-one. So this function itself is not one-to-one unless I make some sort of restriction. And with this particular restriction, it is one-to-one. Now let's talk about this function g. G is the square root of x. Well, we know what that looks like, right? The square root of x looks something like this. But we're going to take that square root of x and move it up 2 units. So 1, 2, it's going to look something like that. Now compare these two graphs here. Notice that if I made the line y is equal to x, they do look symmetric, which is my first indication that these two are inverses of each other. Okay, so what I'm going to do, I can show that this is the inverse function by using that rule of taking, like substituting y with x and so on. I want to do more of that later. Right now what I want to focus on is finding the domain and the range, and then talking about if we compose them, like the problem asks us to do, just composing them. So let's find f composed of g of x. So this is f with g plugged inside, which is f of square root x plus 2, which is, okay, so we're going to put inside f, which is x minus 2 squared. That's the function f. And I'm going to put square root x plus 2 here. So you can see this and this cancels, and I get the square root of x squared, which is x. So that works. Now if you do g composed of f, of x, you're going to get g of f of x, which is g of this x minus 2 squared. So I'm going to put that in that square root. So I get the square root of x minus 2 squared plus 2. I have 2 of these, and I'm taking the square root, so that leaves me with 1 of them. And I have x. So that does work. Now we wanted to talk about what we need to take out of the domain. That was part of this problem. What values need to be excluded from the domain of f and the domain of g? Well, first off, we're told that the domain of f has to be greater than or equal to 2. So we can write that in interval notation like this. Look at the domain of g. This function is a square root function, and we can't put anything less than 0 here. So the domain of this function is 0 to infinity. Because these two functions are inverses, you can tell me that this function, without even looking over here, you can say that this function, its range is 0 to infinity. And you can tell me that the range of this function is 2 to infinity because they're inverses. All right. I wanted to do one more example because this is kind of a complicated example, as you can see. So maybe we'll just do f composed of g, and then you can do g composed of f to double check this. Also notice that I can't really graph this. I mean, I could, but it would take me a while to graph it using those properties of rational functions. It's really complicated. I don't want to graph it. But they're telling us that these two functions are inverses. So let's check it. Let's see if f composed of g is equal to x. Is that true? Well, f composed of g of x is equal to f with g plugged in. G is 3x plus 5 over 1 minus 2x. Okay, so wherever I see an x in this function, I'm going to put this. Okay, so here's an x, so I'm going to put 3x plus 5 over 1 minus 2x. Subtract 5, that's the rule here. And then 2 times this thing. Zoom out a little bit. And then we add 3. So wherever I saw an x, which was here and here, I put this function. Okay, now we have to simplify this. Now this is not going to be fun unless you like to do fractions or whatever, and it's easy to make a mistake, so be very careful. How you want to simplify is you want to combine these two fractions at the top and then combine these two fractions at the bottom. Let's start with the top. Now in order to add these, this is the same thing as negative 5 over 1. So we have 3x plus 5 over 1 minus 2x, subtract 5 times. We need the same denominator, so I need to multiply this negative 5 over 1 with 1 minus 2x over 1 minus 2x. While we're at it, let's go ahead and try to get this one done as well. I'm going to move in that 2 into the numerator here. So this is 6x plus 10 over 1 minus 2x plus 3 over 1. And I'm going to have to multiply this one on the top and the bottom by 1 minus 2x. Okay, let's go over here, make some room over here. All right, so what can we do here? On the top, we're going to get 3x plus 5. Distribute this negative 5 to everything. We get minus 5 plus 2x, all divided by 1 minus 2x, simplifying this top part. Divided by, on the bottom, we have 6x plus 10 plus 3 minus 6x, I believe, all divided by 1 minus 2x. Okay, so let's simplify it a little bit further. On the top, we have these two cross out and we're left with just x. On the bottom, we have 1 minus 2x, and this is divided by, here this 6x cancels. Let's just make sure I didn't make a mistake anywhere. 6x plus 10, and then I have this 3 minus 6x, that looks good. And then on the top, give me just a second. I don't think I made a mistake anywhere. You can double check my work, but what I ended up with on the top was x over 1 minus 2x, and on the bottom I'm going to end up with 13 over 1 minus 2x. And when I finish this, I'm going to take this fraction and multiply it by this one flipped upside down. That's how we can reduce this. And what I ended up with was x over 13. Now, if these two functions were inverses, when I actually do this flip, I should just end up with x. I don't know if I made a mistake. I don't think I did. But because I didn't end up with just x, these two are not inverse functions. So because of that situation here, because they're not inverse functions, now you can't, if you get that f composed of g is x and then the other one g composed of f is not x, then they're not inverse functions. You have to have both of them being x. And since one of these is not x, I don't even have to check the other composition because they both have to be equal to x for them to be inverses. So my math, I ended up with x over 13. So unless I did something wrong, and please let me know in the comments if I did, these are not inverse functions. Okay, let's move on. Okay, so here I have 4 problems I want to do. It says, in these problems, the function f is 1-to-1. So we don't have to check that these functions are invertible. They're letting us know that they are. They want us to find the inverse function and check our answer. Then they want us to find the domain of f and its inverse and find the range of f and its inverse. We're going to do that as well. And then we want to graph f, f inverse, and y is equal to x on the same coordinates. And we're going to start with problem 52. Okay, so we have f of x is equal to negative 4x. Let's go ahead and start graphing. This is the equation of a line. The domain and the range, because it's a line and the slope is negative 4, it goes through 0, and the slope is negative 4, so it's up negative 4 and over to the right. It's up 4 and to the left 1, sorry. So the line is going to look something like this. We don't even have to be very careful, but it looks something like that. The domain of a line is always all real numbers, unless the line is horizontal or vertical, but that's not happening in this case. And the range is all real numbers. Okay, let's graph the line y is equal to x. It's going to look something like that. Now let's find the inverse of this function. Let's do it in red. So how we find the inverse is we switch this f of x, make it y, and then we switch y and x. So this is x is equal to negative 4y, and then we solve for y. So y is equal to x over negative 4, which is the same thing as y is equal to negative 1/4 x. Now, if you want to be very careful with this graph, you go up 1, 2, 3, 4 over 1. So let me just do a better job of graphing this. The graph would look something like this. Now let's graph this inverse function in red. So the slope is down 1 and to the right 4, or you could think of it going up 1 and to the left 4. 2, 3, 4. So right here. And then you could also do the same thing over here. So the graph is going to look something like that. And these should be mirror images. This piece here, you can see that it's pretty close to this line here. Well, this piece is also close to that line. And then this piece close to this line, but it's like to the over here. So it's going to be above on this side. Because this equation is the equation of a line, you can say that the domain and the range is all real numbers. So that one was pretty easy. So we're done with this one. Let's move on to 56. So 56 says f of x is equal to x cubed plus 1. Let's go ahead and start graphing this. X cubed was one of those functions that we had to memorize, the parent function. This is the line y is equal to x. X cubed looks like this. And see how we have this 1 on the outside? We move it up 1 unit. So I'm going to do, I guess I'm going to put it in white. So we're going to go up 1. So the graph is going to look, and we should probably be careful right around here. So this graph goes through 0, 0, 1, 1, 2, 2. This point is 1, 1. This point is 2, 2. If I plug in 1, I get 2, 1, 2. So, okay. So it's going to look something like something like that. So you can kind of go ahead and guess what the inverse function is going to look like. I am going to find the inverse by setting this equal to y, and then reversing x and y, and then we need to solve for y, which means I'm going to move the 1 to the other side, and I get y cubed is x minus 1. And now I need to get rid of that cubed. And to do that, we're going to take the cubic root of both sides. When you take the cubic root, you get this function here. So this is going to be your inverse function. Okay? This function, I think we also had to memorize. This function looks something like this. And it's been moved to the right 1 unit because inside of the x, we're putting a -1. So that's moving it to the right one. So then the graph is going to look something like this. Try to get it to go through the same point here. So something like that. So this will be the graph of f inverse, and this is the graph of f. I want to mention, I don't want you to make this mistake, that f inverse is not the function f so being divided by 1, if that makes sense. So what I'm saying is f inverse, let me put it down here, because this is really important. I don't ever make this mistake. F inverse of x is not equal to 1 over f of x. This is just a symbol for the inverse. So don't take this function and put it under 1. You can see that 1 over x cubed plus 1 is not what we found for the inverse. Okay. Let's talk about the domain and the range. Well, we could look at the graph and tell the domain and the range. But let's just look at the function. This function here. Do we have any square roots or fractions? No. So the domain is all real numbers. And because its domain is all real numbers, the range of this function is all real numbers. Now let's talk about the domain of this function. Just looking at it, do I need to take anything out? Notice that this is a cubed. As long as it's an odd power, you can plug whatever you want under this root. But if it was an even power, you would have to not plug in negatives. Like you couldn't have this thing as a negative. So its domain is all real numbers. And again, you can tell it from the picture of the function. And because the domain of the inverse is all real numbers, the range of this function is all real numbers.